Okay, so what we will study now is the Compton effect. So to study the Compton effect, we need two formulae. One is, what is the energy of a particle of light? It's given by h bar omega. Omega is the angular frequency. Omega is related to the frequency by this formula. And h bar is the rationalized Planck's constant, also known as Dirac's H. These days it's called h bar. And when people say Planck constant, they probably mean h bar, except in Stranger Things. The other thing that we need is the formula for the momentum of the electron. So the formula for the momentum of the of the photon. The momentum of a massless particle is given by Einstein's formula. It's energy divided by c. So now if I use in it the expression for energy forwarded by Einstein, then we see that we can write this as the numerator h bar omega divided by c. So what is h bar? We just keep h bar as it is. Omega is 2 pi nu. C is lambda nu. And therefore, the nu's cancel out. And therefore, we get h bar 2 pi by lambda, where lambda is the wavelength. But this thing has a name. This thing is called k, or the wave number. And therefore, we find a new formula, which is the momentum of a quantum particle is related to its wave number by h bar k. Okay, so this is a new formula that we derived by assuming that relativity is true for the photon. Okay. So now let's examine the kinematics of collision. So this is, say, our electron, which is, say, sitting in space, initially stationary. And let's, suppose a photon is coming in that direction. That's a blue line. So this is the initial photon. And after the collision, suppose the photon goes off in some direction like this, and the electron goes off in some other direction like so. Okay. And so this angle is phi, and this angle is theta. They're not necessarily equal. Okay, so this is the path of the initial photon, and its momentum is p naught, is given by h bar k naught. Okay, k naught is the propagation vector. And this is the initial electron. It has zero kinetic energy. And this is the final photon trajectory. And it has some final momentum p given by h bar k. Okay? And this is the final electron, and it has some kinetic energy. Okay, so this is the picture. So what are the kinematical equation? Well, first, note that this is an elastic scattering. No new particles are being made, right? So it's an elastic scattering. That means that the initial kinetic energy and the final kinetic energies are preserved. And so what is the initial kinetic energy? Well, it's H omega naught. Okay, someone wants to come in. So it's H omega naught is the photon kinetic energy. And then we have, well, it's actually the total energy that has to be conserved, right? And the electron, because we're now dealing with a relativistic particle, the electron has some rest energy, right? Which is given by the mass of the electron times c squared. And then the final energy is h bar omega, the energy of the photon, and the energy of the electron, which let's just write E, where E is given by PE, the momentum of the electron squared, c squared plus me squared c to the power 4 and the positive square root of that, right? Okay, so this is the relativistic expression for the energy of a particle. So this is, say, equation number 1. So this is one equation. Then what are the other equations? The other equations would be the equation. So this is energy conservation. But we also need momentum conservation. Of course, momentum conservation is a vector equation, and there's only the electron doesn't have an initial momentum. So the initial momentum of the system is h bar k naught. Final momentum of the system is h bar k plus p of the electron, right? So this is, say, equation number 2. Okay, any questions about these equations?
Sir, omega naught
No,
is
sir.
frequency.
Yes, omega naught is the frequency of the initial, angular frequency of the initial photon.
So is this different from nu?
Yes, I defined omega here.
Oh, okay. Sorry, I joined late.
No worries, yeah. Omega is the angular frequency, okay? So it has the interpretation of something going around a circle. It's, yeah. Okay? So
Okay.
from number 2. So any more questions?
No, sir.
Okay. So from number 2, what we can do is that we can, okay. So from number 1, what we can do is that we can take the square of that equation, okay? So if I take square of the equation, but before that, what I do is that I take this guy and move it to this side, and I take this guy and move it to this side, okay? And if I take the square, then I get, I get h squared, and then omega naught squared plus h squared omega squared minus 2 h squared omega naught. And on the right hand side, we get me squared c to the power 4 plus e squared minus 2e me c squared, okay? Right. So now we use the fact that h bar omega, that omega is related to, now we use the fact that omega is equal to c times k, or omega squared is equals to c squared k squared. Okay. So this is just a frequency, and this is the wave number, and this is the speed squared, right? So all these squared. So this is just a classical expression. We use this, and then this equation becomes, we can factor out h squared. Inside the bracket, we have the wave number k0 squared plus k squared minus 2 k0k, the modulus of k and k0. And on the right-hand side, we have nothing new. We just keep things as they are. MEC to the power 4 plus e squared minus 2e MEC squared. Okay? So this is from equation 1. And then we look at the vector equation, the momentum conservation, and what if we take the square of this equation? Before we take the square of this equation, what we do is that we take this guy to this side. If you do that, if we square this equation, we get an equation which will have the angle between k and k naught, right? Because k naught and k are vectors here.
Sir,
So really,
shouldn't there be a c square in the last equation?
in this one? Yeah,
Yes,
you're
in
right.
the
That's very good. Yeah. And then we can cancel this, and this will become 2. Very good. Thank you. Somebody's awake. Okay, so if I do that, then what do I get? I get h squared. And then I also get, again, h squared. And then inside the bracket, we get k naught squared plus k squared minus 2, the dot product between k naught and k. And on the right-hand side, we get pe squared, right? And then we can multiply both sides by c squared. So now we have these two equations. So this is equation, say, A, and this is equation B. And we can then subtract these two equations, right? Actually, I don't need the c squared here because I've gotten rid of c squared in the previous equation, right? So yeah. So if I now subtract these two equations, what do I get? On the left-hand side, I get 2 h bar squared k naught k 1 minus cosine of theta. This cosine of theta comes from this term, right? So this guy and this guy, like these guys will cancel these guys, right? And what do we get on the right-hand side? In the right-hand side, we get 4 of these terms, right? So we get so we are basically doing B minus A. So if I do that, then on the right-hand side, I get PE squared minus ME squared C squared. And then I get plus E squared. But E squared is nothing but P squared, PE squared, C squared.
Sir, it should be e square by c square in A because we were dividing by c square on both sides.
We were dividing on c squared on both sides. So yeah, I forgot the c squared here, right? Yeah.
Yes, sir.
Thank you very much. Yeah. Then there should be this c squared should not be there. No, it should just be c squared. Sorry. M squared c squared, right? And this should be just this, right? Okay, good. Okay, so
Shouldn't that be minus since we are subtracting A?
yeah. and then 2 plus 2e me. Okay, do you agree?
Yes,
Did I
sir.
make a mistake?
Yes, sir.
Okay, so this will cancel this. Right. Okay, good. So now let's rewrite this. Let's divide by 2h squared. Then on the left-hand side, we get k0, 1 minus cosine of theta. On the right-hand side, we have me by h squared. And inside the bracket, I have e minus mec squared, right? Okay.
So 2e.
No, the 2 will cancel because, yeah, you're right. Yeah, it's going to be, hang on, then did I make a mistake? Yes, I did. Just 1 second. Yeah, because there was a 2e here, right? So, just 1 second.
Sir, we are dividing by 2h bar square, so the 2's will cancel out. But it would be mec square divided by
MEC square
2.
would have divided by 2, right?
Right. Let me just see. There are actually 2 factors of me squared, which I forgot before. So there's when I did b minus a, there was this term, and a had this me squared, which was this term, but this guy should have also given me an me squared, right? Because this
Yeah,
is
they
minus
wouldn't
p
cancel
squared.
out each other.
Yeah, and then
Because
there
they
would be a
would the same
minus,
size. Yeah.
minus me squared, sorry, c squared, right? Yeah, coming from this guy. So I missed that, and because of that, there would be a 2 in front of this. So when we divide by 2, all the 2's will go away, right? Okay.
Yes, sir.
All right. Okay, so now what we can do is that we can say, okay, what is this? From our energy equation, somewhere above, we see that E minus me c squared is h bar omega minus h omega. So we can replace the thing in the bracket on the right-hand side by me by h bar omega naught minus h bar omega, right? We're using the energy conservation equation from way above. So so now we can rearrange this again. This can be written as, okay, let me just do one more step, me by h squared. This can be written as h bar ck naught minus h bar ck. Then 1 minus cosine of theta is going to be me by h bar squared. And we can factor out the h bar c, and inside it'll be 1 over k minus 1 over k naught. Okay, we have divided k by k naught on both sides. So, of course, then one of these factors will cancel out, and then, sorry, this is, yeah. And then what we can do is that we can now transform, because we want the frequency dependence, right? So we can change the k dependence to omega dependence. And if you do that, this mec squared by h bar And then we have 1 over omega minus 1 over omega naught. So this we can rewrite as 1 over omega is equal to 1 over omega naught plus h bar by me. We have cross multiplied things. Me c squared 1 minus cosine of theta. And then we can transform things into nu. The nu is going to be given by, if you just do one line of algebra, is going to be given by nu naught, which is the initial frequency, divided by 1 plus h nu naught divided by me c squared 1 minus cosine of theta. Okay, so and this is the famous Compton scattering formula. And to make sure that we didn't make any mistakes, you can see that dimensionally, well, we can still make mistake. This has the dimension of energy. This has a dimension of energy, right? So they cancel out. The dimensionally, this is dimensionless. Okay, so this is the Compton scattering formula, and it describes, accurately the direction or the angle dependence. I guess there shouldn't be a angle dependence of the scattered photon. Okay, so this is like algebra, right? I mean, the idea was clear. We just did the algebra with the kinematics, and we derived an equation, and using input from both quantum mechanics and special relativity. Okay, any questions? So let's look at the the picture again, because this is the angle. So backscattering is when things are backscattered. What's the value of theta? It's 180, right? So when
More than
things are
90 degrees?
Yeah, so it's 180. Well, yeah, exactly. So the photon that is completely backscattered, so cosine of 180 is going to be -1, right? And front scattering is cosine is theta is 0, and so the frequency in the front scattered is the same. The frequency of the backscattered angle is frequency of the backscattered photon is reduced, right? And everything in between. Okay. All right. So any questions so far on this?
And that matches the experimental evidence, right? Or experimental data.
Yeah, otherwise Compton would not have gotten a Nobel Prize. I think he did get the Nobel Prize for this, yeah. I mean, this is like hilarious in one sense that, it's a calculation you can do at the back of an envelope and get the Nobel Prize from it, right? But of course, conceptually, it's extremely deep. And that's the thing, is that, yeah. Okay, somebody sent a question, I think. No questions. Okay, if not, let's move to the next topic, which will be a slightly philosophical